Good afternoon. Welcome to today's webinar from SCA with Dr. Steve Sonnenberg on unconventional petroleum systems from deep basin to tar sands. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. And so I'm going to start some polling questions. So the first question, as I launch it, is what's your primary discipline? So we'll ask the audience to answer whether they're petroleum engineers, geoscientists, facilities engineers, petrophysicists, or other. Looks like we have a large contingent of geoscientists, probably 2/3, and followed thereafter by petroleum engineers, another good group. Looks like most of you have voted now, so I'll go ahead and close that poll and share those results. We have 61% geoscientists, 22% petroleum, 9% in petrophysics, and a few in the other groups as well. So let me launch the next poll, and that's how many years of full-time experience do you have in the oil and gas industry? So we're getting our responses pretty quickly here, and looks like the results are coming in with a somewhat bimodal distribution. Most of you have, well, not quite most, but 46% have over 30 years. So let me close and share those results. And then quite a few in the other categories as well. The lowest category is those with less than 1 year, but a good distribution among the others. From today's audience today, we have a good distribution from around the world in addition to the United States. Our audience, our registrants were from Nigeria, from the UK, Argentina, Barbados, Canada, the UAE, Brazil, and Pakistan. So before I introduce Dr. Sonnenberg, I'd like to remind you that you are muted during this webinar, but you can ask questions during the presentation using the GoToWebinar question feature. We'll cover the questions and hopefully some answers at the end of the presentation, and of course you will be anonymous as you ask your questions because I will be reading them. So feel free to start to type in your questions throughout the presentation so that we can start to answer them at the very end of the webinar. So I'm going to go through some opening slides here, and as I mentioned, this is the webinar on unconventional petroleum systems from deep basin to tar sands. And Dr. Sonnenberg is a professor and holds the Charles Butcher Distinguished Chair in Petroleum Geology at Colorado School of Mines. And he has a number of specialties. He's originally from Montana, but has degrees from Texas A&M and Colorado School of Mines, and more than 25 years experience in industry. He's served as president of several organizations, including the APG, the Rocky Mountain Association of Geologists, and the Colorado Scientific Society. He's also served on the Colorado Oil and Gas Commission and was actually the chair of the commission. He's received several awards throughout his career, and in 2013 was awarded the Halibuty Medal from APG. So the webinar today is an excerpt from a workshop that Steve teaches for SCA on unconventional resource plays. The workshop is being offered in Houston in May and November, and so you're welcome to register for those dates now. If you're not in Houston or don't find it convenient to come those dates, we can schedule it in-house at your location. Just contact us. And we have a number of these webinars featuring our instructors throughout the year. So the next ones coming up include Jennifer Miskimmons. She'll be speaking on fracture conductivity in March. Raymond Woodward will be speaking also in March on geosteering. And we have Jim Smolin scheduled in April on production logging. So be sure to register for one of those events coming up if those are of interest to you. And again, SCA, in addition to training, we also offer consulting, direct hire services, and we do projects and studies for many of our clients. And so I'm going to turn over the presentation rights to Steve. And Steve, I'll let you get started with your presentation.
Okay, so
I think we're still waiting to see your screen.
Yep, I just clicked on it. Sorry about that.
Okay, good.
Can you see it now? Nope.
Not yet.
It is just that little arrow, isn't it?
Yes.
Show the screen.
Now we see it.
Oh, you do?
You've got it. Yes.
Okay. Well, technology works. I take it everyone can see the screen now. And not hearing anything from Susan or Mary, I'm assuming we're good to go.
Good to go.
So I have several slides put together on unconventional reservoirs, and I'll take you from really deep basin settings all the way to more tar sands in the little journey that we'll take today. So we'll cover a number of things, have some general comments to begin with, talk a little bit about continuous and conventional reservoirs, and then touch on all these topics: tight oil, heavy oil, bituminous or tar sands, oil shale, tight gas, shale gas, coal bed methane, biogenic gas, and last but not least, gas hydrates. Would point out that textbook on petroleum geology that Richard Selly and I did in chapter 9, we cover off on these systems, although we call them non-conventional systems, but a book that perhaps might be of interest to you. So the question that first comes up is what makes it unconventional? And part of that is the quality of the reservoir. And we can actually be very tight or very porous, but the very porous ones are generally in the category of tar sands and so on. The type of trap is more continuous, so covers a large area. Reservoirs are quite heterogeneous, both in conventional and in unconventional. The state of the hydrocarbons, solid, gas, liquid, tar, sorbed, and so on. Many factors control production, and then factors also impact the occurrence of the hydrocarbons. There's a story on viscosity and permeability associated with these reservoirs, and of course, technology is required to be able to produce these unconventionals. So a slide which I've dramatically modified from Les Magoon with the USGS, in which he brought up the petroleum system concept, but we can go from the deep basin where we have unconventional settings. About the middle of the slide, some conventional reservoirs where we actually have oil sitting on water and so on. And then up dip from that, we can go into unconventional degraded, and that's either water washed or biodegraded reservoirs. That'd be heavy oil and tar sands. And in the deep basin, we have the whole gamut of things from tight oil, tight gas, shale gas, and so on, and perhaps a little bit shallower biogenic accumulations, oil shale, and coal bed methane accumulations at various depths. So we can look at a diagram which looks at gravities of hydrocarbons, and then we can also see what the corresponding viscosities are, and then in general what some of the permeabilities are for some of these systems. So in the heavy oil and tar sands, those are quite porous, but the viscosity is quite high. And then we get into tight oil reservoirs, and we have a mid-range of permeability or low-end permeability and various viscosities. And then the tight gas reservoirs, generally we have very low permeability, but the viscosity, of course, is that of gas, which is very low. So that's part of what the story is all about viscosities and permeabilities. Unconventional characteristics, the recoverable reserves are very large, many of them around the world. Takes a lot of capital to get at these. The recovery factors generally are low. And then there's environmental issues which can easily be overcome with technological ingenuity too. So we will kind of work our way through this resource pyramid today and be working on the midpoint of the pyramid on down. On this pyramid, I've divided it into oil versus gas reservoirs, and we'll touch on all of these. The very bottom of the pyramid, oil shales are yet to be economic, at least in the US, and then gas hydrates are in various stages of development, but all the rest of them are in stages of development when we go a little higher on the pyramid. Because technology is required to get the production from these units, we term them as technology reservoirs. We can look at the type of unconventional and whether it's tight oil or gas hydrates. You can see all of these systems need some sort of a technology, and therefore the reason that we call them technology types of reservoirs. All these systems, it all starts with the source rock and having an adequate source rock, and then being either generating oil or gas, and then those hydrocarbons can migrate into conventional traps, or much of it can stay in the deep basin setting or migrate into real shallow traps where it can be biodegraded and so on. And in addition to that, we can have the biogenic types of accumulations too. Type of organic matter is important in many of the tight oil and gas plays as we see them. And you can see from this list right here that the vast majority of plays in North America, and one listed for you in South America too, are largely type 2 kerogens. The one exception on this list is the Green River from the Uinta Basin, which is a type 1 kerogen. So the type of organic matter is important. These things initially generate oil, and with sufficient burial, that oil can crack to natural gas. Source beds are plentiful around the world and plentiful throughout the geologic column. So this just illustrates the stratigraphic distribution of major source rocks after Olmec and Clemmy, and then also the distribution of major reservoir rocks associated with those source rocks. Some migration does take place, of course, within those units, so it doesn't compare one-to-one. The concept of burial history and what happens when we bury source rocks and then convert kerogen to bitumen to oil to condensate to gas is one which has been reviewed previously by Meisner and Momper, but in general, the creation of overpressuring associated with hydrocarbon generation and such. Just some general comments. At the very top of the diagram on the left, there's also this bacterial methane, or the biogenic gases that can also occur in some of these areas. One of the other aspects of all of these plays is structure does play a role, and understanding the types of faults, fractures, and so on that are present is quite important. And what is that direction of your maximum principal stress? And in order for you to drill your horizontal lateral in the proper direction. Also important in all of this is perhaps the conversion of kerogen to hydrocarbons and such, and the initiation of microfractures associated with that. So a diagram from Tissot and Velty, 1984. When we also look at many of these systems, as I go through just probably my last introductory slide here, we know that the systems themselves are what we call, in Deep Basin anyway, inverted systems, where we actually have water that sits on oil, sits on wet gas, sits on dry gas. Reservoir quality diminishes dramatically as we go from shallow to deep in any of the basins. And then the types of porosity systems that we end up having in many of these areas ends up being the interparticle, the intraparticle, fracture pores, and also organic matter types of pores. So many inverted systems around the world, and I could put on 20 other illustrations like this, but everything from the Eagle Ford all the way to the Biogenic and the West Siberia Basin illustrated on this particular diagram. Sweet spots in many of these plays end up being a function of depositional environment, also how much diagenesis has taken place, and then what is the abundance of fractures, and those items can come together and help create a sweet spot. So the elements then that lead to a successful oil and gas play are largely start with the source beds. So thick, organic rich, have them mature. That all leads to hydrocarbons in place. The shales themselves should have a mineralogy that generally is not real high in clay content, and that can lead to brittleness. Maturity can also lead to high pore pressures, and all of these factors then can lead to productivity. So on the unconventional light oil ends of things, we can tend to look at those in these three quadrants: the tight shales, in which we don't probably have a lot of fractures present. Maybe an example of that would be the Eagle Ford fractured shale. Well, one of the better examples that I can come up with is the Pierre Shale down in the Florence Canyon City area. Then we get into the hybrid systems, where we not only have the source bed, but then we also have the tight reservoirs adjacent to that. So we call those the hybrid shale systems. And two excellent examples from the Rockies are the Bakken and the Niobrara. So the plays associated with tight oil are several across the U.S., and you can read on the lower right-hand part of the slide everything from the Austin Chalk to the Eagle Ford, Bakken, Niobrara, the Permian Basin, of course, with us, all of its activity these days. One that's in its early stages still is the Mowry, and the Monterey has seen mixed results to date on the tight oil accumulation. Also, although a great source bed, they're not all of them are performing up to their initial expectations. Kind of an interesting diagram to look at is the top 100 U.S. oil fields as forecast by the EIA, and also a map illustrating where those occur. And the interesting thing for me is when you look at this list, at least 4 of those are within the unconventional arena: the Eagle Ford, the Sprayberry, the Wattenberg field of the Denver Basin, and then the another Eagle Ford example. So just touching on some of these plays as we look at them, and I'll take you from tight through the oil ones and then move more into the gas ones. About one that we have extensive knowledge about is the Bakken of the Williston Basin, and it's a system that extends on up into Canada, but late Devonian, early Mississippian petroleum system, which has generated enormous amounts of oil and gas, and the technical recoverable numbers, according to the USGS latest assessment, 7.4 billion barrels, 6.7 PCF. There's many things that control this petroleum system and what makes it so good, but it all starts with world-class organic rich source products, which average 11 weight percent, and that has led to oil generation of anywhere from the people who have estimated the amounts generated from 10 billion to 400 billion barrels of oil. There are several targets up in the Williston Basin: the middle member of the Bakken, the upper Three Forks, a brand new member which was described recently by Julie Lefevre as this pronghorn member. And the system is overpressured, and that overpressuring is related to hydrocarbon generation. Of course, I don't have time to go into any detail at all on any of these systems, but just touch very briefly on all of them. Heavy oil deposits and or tar sands exist around the globe too, and perhaps the best known ones are up in Canada, the Athabasca types of deposits where there's over 1 trillion barrels technically recoverable, and that overall production in Canada is 2.7 million barrels of oil per day. Gerard de Masson in 1977 just put together a cross-section illustrating where the heavy oil and tar sands accumulated from deeper source rocks and migration then into the shallow reservoirs where they're degraded, water washed, and biodegraded, which results then in the very low API types of gravities. There's many technologies that are used to get at those types of oil, and the three basic ones illustrated on this slide is more of a surface mining, an ex situ process, and then the subsurface processes, steam-assisted gravity drainage, SAGD, or the cyclic steam stimulation, CSS, both of which have contributed greatly to the overall oil production in Canada. So those extraction techniques, again illustrated on this slide, from mining to the ex situ to the in situ processes. You can see that the overall Canadian oil sand and conventional production, how it charts out and what the forecast is out to 2030, and the overall major growth that's envisioned for Canada is within these oil sands and the heavy oil deposits. And so perhaps taking that 2.7 million barrels of oil per day production and increasing that quite dramatically over time. Oil shales themselves are thermally immature, so they require artificial heating. The oil shale resources around the world are quite abundant, and perhaps the lion's share of all of that happens in the Green River Formation of southwest Wyoming, northwest Colorado, and the Uinta Basin. So if we zoom into that area, everything associated with the Green River Formation, we can see what the in-place numbers end up being in the Piceance Basin. Ends up being one that we study extensively, but is thought to have anywhere from 1 to 1.5 trillion barrels in place. So of course, that's in place, and then what kind of technology do you use to get that oil out? So a stratigraphic column for the Piceance Basin illustrates this Green River can be broken into a Garden Gulch and a parachute member, and there's lean and rich zones of oil shale throughout that interval. And work by Denny in 2006 illustrate then what the numbers are for the shale oil resources, and you can get over the 1 trillion barrels with each of those rich and lean zones as illustrated on that slide. So technologies to get that oil out is in some ways similar to the heavy oil tar sand deposits. We have ex situ and in situ types of processes illustrated from this diagram. And the ex situ processes, mining, retorting, oil upgrading, send the oil to the refinery and everything gets reclaimed at the very end. The in situ process, drilling and site preparation, heating in place, post-production cleanup, sending the oil to the refinery. Oil associated with the in situ process, API gravity around 40, the ex situ process sometimes around 23, so quite a range in the API gravity. The in situ processes, all the big players or have been or are involved in it, from America's shale oil company to Chevron, Shell, ExxonMobil in Colorado in some experimental settings, and then over in Utah, a newer company, the Eco Shale technology being applied to hopefully develop oil shale. So switching then gears to the gas side of things, we can go into the arenas of shale gas, and those types of plays, at least in the U.S., are quite well known. The Barnett, Marcellus, Haynesville, the coal bed methane types of play. The best coal bed methane in the world is the Fruitland coals of the San Juan Basin, and then the tight gas sands. And the best example of that's the Williams Fork from the Piceance Basin, but there are several others in the Rocky Mountain region on this list. The principal types of those reservoir systems then again shown, and part of what controls that gas production is the nature of how that gas is held in those particular units. And coal bed methane is principally a sorbed gas. Coal gas shales largely a sorbed gas, and tight gas sands partly sorbed gas. We can also do like we did with oil and look at this case, the top U.S. gas fields, and this just happens to list the top 10, and then a map at the very bottom which illustrates the distribution. And in this particular case, you see the red stars are plentiful, showing that most of the major gas accumulations are unconventional. Everything from the Marcellus to the Barnett to the Fayetteville to the San Juan Basin to the Haynesville to the Jonah Reservoir in the Greater Green River Basin to the Wattenberg Field and so on. So shale gas plays are everywhere across the U.S. It all started with Mitchell Energy and George Mitchell in the Fort Worth Basin and the Barnett, and that later went to things like the Haynesville and the Marcellus and the Utica, and there's just a whole number of these plays then across the U.S. The significance of some of those accumulations is illustrated by this particular slide, which just illustrates the Marcellus gas play from the Appalachia Basin. And there's a whole bunch of different people who have estimated how much gas is actually present in the Marcellus, and I've just highlighted a couple of them in red. But if you believe those numbers, anywhere from 360 to 410 trillion cubic feet associated with this unconventional shale gas accumulation, making it one of the largest gas fields in the world. Tight gas sands are also plentiful across North America. All these unconventional plays get lots of work from industry in North America, and that work extends into Canada and down more recently into Mexico too. And one of the ones that I'll illustrate for you in very briefly will be from the Piceance Basin, the Mesa Verde interval. The systems themselves for tight gas are low porosity and low permeability, and you can see what the porosity permeability ranges for the tight sandstones, and it also compares what the shales would be, which is even lower than the sand. So typically we have low perms and low porosity within these systems. The basin center gas accumulations across the U.S., according to Ben Law in 2003, many of the basins had the potential for these types of accumulations, and the way he defined the unconventional systems at that time was everything less than 0.1 millidarcy fell into this category of the unconventionals. What traps the gas are probably these pressure seals, as is indicated in the upper right-hand slide by Sturdom. So jumping into the Piceance Basin, one of the richest gas basins in North America, a slide by Urowitz in 2008, illustrating in this Mesa Verde interval many fluvial sandstones, all gas saturated within the Williams Fork formation of the Mesa Verde group, and then below that the Isles Formation, also significant gas accumulations. More recently, there's gas and oil that's been found down in the Niobrara interval within this Mancus shale package. And together, those end up being a huge resource potential for the Piceance Basin. The Mancus Shale, according to the USGS, recent estimates is 66 TCF of gas. And the Williams Fork, based on work from Steve Camella and others, may be in the range of 90 to 100 TCF of gas within this Piceance Basin. So you can add those two together and end up with an enormous amount of gas in this relatively confined basin in the Rocky Mountain region. The map on the right just illustrates structure and then also the thickness of the continuous Williams Fork gas accumulation. Coalbed methane is something that's still important, and it has seen quite a bit of activity through the 1990s and into the 2000s, and perhaps some of that activity is not as active as some of the other plays currently. But coalbed methane largely producing, as I just said, methane, and methane represents 90% of the gas volume, so we can have some heavier hydrocarbons, and the coals themselves are capable of absorbing large quantities of gas, 600 standard cubic feet of gas per ton. Gas storage mechanism, free gas, dissolved gas, adsorbed gas, that equals the total gas that we can then produce out of coalbed methane types of reservoirs. Coalbed methane reservoirs, the best gas production comes from these high volatile, medium volatile bituminous types of coal. When we compare that to more of the traditional type 3 and type 1, type 2 types of reservoirs. And in all of these, biogenic alteration of organic matter can also contribute significantly to the hydrocarbons that are present. Factors affecting coalbed methane producibility involve all of these, from gas content of the coals to the permeability, what type of groundwater flow do we have, what is the coal rank, what's the coal distribution, how thick is it, what's the structural and depositional setting, and so on. And just an example of one of the coalbed methane fields in the Rockies, and there are several, but this from the west side of the San Rafael Swell, the Drunkard's Wash field, illustrating coal thickness, and then also a cross-section through the Farron interval and that distribution of coals in this particular case. Switching gears yet once again and going into purely biogenic gas, the shallow biogenically derived gas forms in a sand or a chalk or a shale sequence. We consider it unconventional because it's not thermogenic in origin. It is more or less structurally controlled in many cases, but we throw it into this unconventional category because of the nature of how that gas is actually generated. So when we look at a maturity diagram, of course, thermal maturity of source rocks and temperature ranges in which we can find oil or dry gas, and the biogenics are where we have fairly low temperatures within those reservoir units. One of the most classic areas of biogenic accumulation of gas occurs within the Niobrara Formation, and in eastern Colorado, there's a number of structural fields, many of them found by John Lockridge back in the 1970s. And most of the gas production in this area on this map comes from the very upper part of the Niobrara in what's called the Beecher Island Zone, or what we might call the upper chalk in the Niobrara, or the Niobrara A interval. So it goes by a variety of names. And then as you get deeper into the Denver Basin, the accumulations end up being thermogenic within the Niobrara. So the Niobrara is perhaps one of the most interesting petroleum systems within the Rocky Mountain region, since it has both of those components to it. And then the last thing that we'll just touch on very briefly are these gas hydrates that are around the world, and the one person that I know of who is the world expert on these, Tim Collette, and published extensively on these units, and a couple of his diagrams, one illustrating this gas molecule trapped within this water molecule cage, and then the gas hydrates accumulations, both where it's been recovered, gas has been recovered, and then where gas is inferred. So a variety of depositional settings that range from permafrost types of settings to deeper marine types of settings to control the occurrence of these gas types of hydrates. There have been many estimations of how much gas actually is present within gas hydrates, and those change significantly over time. And then the ranges that you can see on this particular slide from terrestrial to oceanic gas hydrates ranges anywhere from 100,000 TCF to 300 million TCF of gas. So the quantity in the resource pyramid is potentially enormous for hydrates. Switching gears back to what the EIA has said about gas and oil production in the U.S., you can see forecasts for natural gas and then forecasts also for oil. And when we look at the forecast for natural gas going out to 2040, most of the increase in growth through the year 2040 is all with unconventional systems, shale gas, tight gas. And we can do the same thing for the oil production. You can see what non-tight oil is doing, and then all the tight accumulations, again, resulting in oil production, perhaps giving the U.S. over 10 million barrels a day production through 2040. So there's a whole bunch of things to cover on unconventional systems, nothing in great detail, but the course does that in great detail. But these unconventionals that we've just gone over cover the bottom part of our resource pyramid. Technology, of course, just plays a huge role, helps to have a high product price to make everything economic, because these types of plays are very sensitive to oil and gas prices. Overall, in the US and in Canada, these things have been huge game changers for production, and all of these types of units have worldwide potential. So with that, thank you for your attention, and be glad to answer a couple of questions.
Great. I want to remind our audience that you have an opportunity now to pose your questions using the question feature in the GoToWebinar dashboard. Steve, can you talk about recovery factors and what are the best potential for increasing recovery factors? Many of these plays are in the low teens or even single digits on recovery factors.
So this is an excellent question, and it all depends on what type of unconventional that you're in to begin with. But the tight plays, tight oil, and even some of the tight gas, they have different recovery factors, but the tight oil's probably in the 10 to 15% recovery factor range, and the 15 might be on the real high side. Tight gas is higher than that, of course, but then we get into some of the tar sands and heavy oils, and it depends on what kind of technology that we use, and the same would apply to oil shales that we apply to get that oil out. So if we use a mining technique, surface mining, our recovery factors can actually be quite high. But if we are using some in situ type of technology, then those recovery factors go lower again. So it all depends on the type of technology used and the type of play one's looking for. But the basin center types of accumulations, generally the recovery factors are on the low ends of things, and that mandates many wells being drilled to adequately obtain that resource.
Are we beginning to see the impact of improved geological characterization on reducing the rapid well declines in unconventional reservoirs?
So geologic reservoir characterization, which is a favorite topic of mine, a class that I teach here at the School of Mines too, involves a lot of things from studying not only the depositional environment, but also the diagenesis, but then also the types and the abundance of fracturing that are natural fractures that are present within these reservoir systems. So combine all aspects of reservoir characterization together along with geomodeling, and then taking geomodels into reservoir models can greatly increase the recovery of hydrocarbons from these plays. So it is something that involves a team of people, from geologists to geophysicists to reservoir engineers, to actually adequately get at what the resource actually is out there and what is ultimately recoverable.
Okay. Next question. How much heterogeneity is in these reservoirs, the unconventional reservoirs, and what are the main controlling factors of these heterogeneities?
So all of these reservoirs are heterogeneous, and in some ways, I think early on people thought that if they tried to develop these things, it would be just like a blanket accumulation. We don't have to worry about the heterogeneity that may be present. But when you study these units in great detail, you will see exactly the same types of heterogeneity being present that are in conventional reservoirs too. And by that I mean pinch outs of sandstone, clay drapes, diagenesis occurring across the area, and so on. So a large amount of study needs to be done on all of these systems, and it all starts with geophysics and geology and forming some sort of a geomodel and eventually getting to a reservoir model perhaps to exploit these systems. But sometimes people wonder why they aren't recovering certain amounts of hydrocarbons and such, and it goes right back in many cases to what kind of model did you start with and what are the types of heterogeneity that you have within these systems. And again, the heterogeneity is everything that you oftentimes see in conventional reservoirs, plus some, because you really have this diagenesis overprint on many of these deeper systems.
Can you talk about the environmental impact of these resource plays?
So the environmental impact, again, is similar to, I would say, other reservoirs too. And all of these systems have potentially some impact, but those impacts can be mitigated. So the types of environmental issues associated with large drilling operations can be noise, dust, traffic issues, and then it can also be issues on completing wells, the flaring of gas and those types of things. And I'd say by and large, many of those types of things are being addressed by operators. And so ultimately, the technology exists to control those impacts. Some of the systems like oil shales, people have envisioned water being a big issue. And again, I would suggest that the technology is available from the various operators out there, and they've tried to address exactly water usage, and then if there are significant issues, then how to mitigate those issues. So I think it goes hand in hand, the development of the unconventionals and the environmental types of things that can come up, but I know that industry addresses both of those. We are all environmental stewards as we go forward on these things.
So what is considered a good density of induced microfractures per square foot?
Of induced, so not natural, but induced, that would probably be covered more adequately in one of your upcoming webinars by Jennifer Miskimmons. So
We'll defer to Jennifer.
Punt on that, but save that question for Jennifer, or whoever asked it should come back and watch Jennifer, because she will let you know about that. The one thing that we do know is the technologies change so dramatically in terms of perf clusters to how much proppant and fluid are used within some of the stimulations, fracture stimulations, that number means that the fracture density keeps getting closer and closer to the induced fracture density, or smaller and smaller.
Next question, should digital core analysis be made the norm for quantification of volumetric and flow properties of unconventional reservoirs, both the tight reservoirs and the shales, rather than using the outcomes of various SCAL and CCA procedures developed for conventional reservoirs?
Of all of these issues, and it's been wonderful not only to see the types of work that we do here at the School of Mines, but also then what all the laboratories are doing. So technology is moving along on not only helping exploit these reservoirs, but it's also moving along to help understand these reservoirs. So absolutely, the changes in the way that we analyze these things in the laboratory are quite significant. And where we are today versus where we were 10 years ago is like an order of magnitude better in understanding the reservoir systems. So all of that is a moving target, as is getting the resources out of the ground on these systems. And so there is a continuous improvement of all the technologies in all the laboratory settings. So absolutely, technology is going to play a huge role going forward, not only in the development of these things, but also then in the analyzing of the cores and such back in the laboratory and the fluids.
So does an unconventional reservoir, such as a shale oil, need a cap rock too? A trap?
So we still believe in the fundamentals of a petroleum system, reservoir, source, seal, and certain amount of migration that can take place. Sometimes the seal or the cap rock can be an episodic type of seal. So the system itself in a deep basin can overpressure, break through that seal, and then with a slight migration of some oil or gas out of the system, those fractures can close back up, or perhaps that seal even heals itself. So all of these things, the fundamentals of a petroleum system still are in play. Reservoir, trap, seal, timing, migration, maturity, all those things are important things for us to take a look at in terms of the occurrence of these unconventionals.
Are there some rules of thumb regarding the base oil price that's necessary for commercial viability of unconventional reservoirs?
I lost the first part of that, but could you repeat that first sentence that you said?
Are there some rules of thumb regarding base oil price for the commercial viability of unconventionals?
As this slide suggests, increased product price is important for these unconventional plays in hand with improving technologies. So that's a bit of a moving target too. So improving technologies can enable you at lower product prices to look for these unconventional systems. If you have high enough product price to begin with, sometimes technology is still playing an important role, but perhaps that product price is what drives you right into one of these systems. One of the uh, examples that we use quite a bit of for just oil prices is the shale oil of the Basin and such. And a lot of the operators who are involved in the in situ or ex situ type of extraction for the shale oil all felt like the price of oil should be around, this is a couple of years ago now, should be around $100 a barrel. And then, of course, the price where it was at 100, we thought that was just about to kick off. And then the price drops to $50 a barrel. And so some of those then become obviously on the uneconomic type of a target. So what then has to happen is some sort of a dramatic improvement in technology or somehow that oil or gas price increase. So they're both sensitive to technology and product price. And I do review what people consider for many of these tight oil and tight gas plays to be the break-even prices these days. And it would appear that many of the plays in the U.S. anyway, when we're around $60 a barrel or $55 a barrel, have reached that break-even price. And of course, back to one of those slides, it's always sweet spots that are out there in all these plays too. And many of those sweet spots are capable of such an enormous amount of production that they're not going to say they're immune to product price, but they're less sensitive to it than perhaps non-sweet spot areas.
So what are the main future expected developments in modeling of non-conventional or unconventional reservoirs, such as the geological representation, the fluids, the physical model? Do you see any real breakthroughs in those areas?
Well, I think everybody these days wants to get the modeling down to the microfracture types of scales and such. So there is dramatic improvements being done on all the reservoir modeling by various units, including the people here at the School of Mines, on moving forward with new innovative modeling systems. So part of it involves not only looking at the physical aspects of the rock, but then is kind of ground truthing what you're doing, but then taking those observations into the various computer models that are being done, code being written to better understand that deliverability and fluid flow through these ultra tight systems. How important is the percent of matrix contribution versus fracture contribution, natural versus induced fractures, and so on.
Very good. So I think we've exhausted the questions from our audience today. We had several very good questions. Thank you, audience. I want to remind you that you will receive a link to the recording of today's webinar that you can share with your colleagues. We'll ask you to fill out an evaluation form. We'll send you some registration details if you're interested for the workshop on unconventional resource plays. That's scheduled in the public format in Houston during the weeks of May 14th and November 14th, but you're welcome to schedule it in-house at a location of your choice at Dr. Sonnenberg's availability, of course. So thank you for participating today, and we look forward to seeing you in March in our next webinar. Thank you. Goodbye.
Thank you.